So I'd like to talk to you today about cosmology and the fate of the universe. And I'd also like to introduce the ideas of dark matter and dark energy. So dark matter, one of the largest things that supported the idea of dark matter was Vera Rubin's work studying the speeds, the rotational speeds of stars in spiral galaxies. So first, let's assume that in a spiral galaxy, most of the mass is in the center, and we'll call that big M. And then let's also consider a star with mass little m, which is a very tiny little insignificant fraction of the total mass of the galaxy. And we're going to say that it's in one of the arms of the galaxy. Okay? So the big M is right here in the middle of this bright picture of the spiral arm, and let's say that our little m is way out here somewhere. Okay? Now, we can consider this to be a decent assumption if the mass of the galaxy scales with the brightness or luminosity that we see coming from that galaxy. In other words, most of the light from the galaxy is coming from the very center of the galaxy. And then, of course, according to Gauss's law, once you get outside of that region, then you can consider it to be sort of a point mass, all concentrated at the center, and then you can look at a little tiny mass, a star, out in one of the arms and consider it to just be the force between two bodies. Okay, that gets covered in classical mechanics, physics 3010. Okay, but let's go back to introductory physics class. You can set the centripetal force for that star orbiting the center of the galaxy. So that centripetal force would be mv squared over r, where m is the mass of the star, v is the tangential orbital speed, and r is the distance from the star to the center of the galaxy. Okay, and now you set that equal to Newton's law for universal gravitation. G, the gravitational constant, big M, the mass of the galaxy, little m, the mass of the star, divided by r squared. Now you can solve for that tangential velocity, and you get V is equal to the square root of G big M over r. Okay, so what this tells you is that if you examine the profiles for the velocities, the tangential velocities of stars in spiral galaxies, then you should see that that velocity is proportional to 1 over the square root of r. So what Vera Rubin did was she examined data of the Doppler shifts of stars in galaxies, and she looked at it, and then she determined from that data the tangential velocity, the tangential orbital velocity. And what she saw was not at all what was predicted by that simple little model that I just put forth. Okay? So if you look at this graph in the other upper left-hand corner here, the blue line, the blue curve, would be what would be predicted by Newton's laws based upon the mass that can be seen through the luminosity of the galaxy. Okay, so the blue curve would predict that. And then the dots, those are data from stars that she actually saw and observed in the galaxy. So she saw these tangential velocities and she plotted them out and saw that it didn't at all match the theory. Well, what that would mean is that the mass of the galaxy isn't concentrated just in the center, okay? That it would have to be spread more throughout the galaxy itself, and that a significant fraction of the mass of the galaxy would be far away from the center of the galaxy. And not only that, if you compare that to pictures and images we have of the galaxy, it would mean that basically we can't see most of the mass from the galaxy. So this was a big point in the favor of the theory of dark matter. So, to quote your textbook here, to supply the required gravitational force, this dark matter must have a mass at least 10 times the mass of the visible matter in the galaxy. That is, more than 90% of the matter in the galaxy is in some unknown and invisible form. This dark matter permeates the region of space occupied by the galaxy and may surround it in the form of a halo. And so if you go online now and look through current research in physics into physics and astronomy into this, then you'll see plenty of discussion about halos of dark matter around galaxies. Okay? Now, what is dark matter? Well, there's a bunch of theories about what it might be. Basically, it falls into two broad categories. First of all, that it might be something called a MACHO, massive astrophysical compact halo object. So these would be astronomical objects that we can't see just because they're not emitting light. And since we're getting information by looking at satellite images of these things from far away, well, if you can't see it, if it's not glowing, we won't be able to see it. Okay, so these include the category of neutron stars, brown and white dwarfs, etc. These things that don't emit light. So that's the MACHO. Now, to counteract that, there's the WMPs. Okay, MACHOs and WMPs. WMP stands for weakly interacting massive particles. Okay. And this is the idea that there are particles out there that we haven't found yet, and we haven't found them yet specifically because they're very, very weakly interacting. And so all the ways that we have of detecting particles are based on the idea that, say, for example, it has a charge or it interacts with matter in some way and then goes through some sort of reaction, leaving products that we can see. But if a particle is very, very weakly interacting, then it might just pass right through matter without interacting with any matter that's in there. And so the odds of us detecting it would be super, super low, okay? Because the cross-section for this particle's interaction with any other particle is low enough that we just wouldn't see it. So that's why they're called weakly interacting massive particles. And there's a number of things within this category of WMPs. The axion is discussed in Crash Course Astronomy videos that I want you to watch. And there's a number of experiments out there, especially in high energy particle physics, that are trying to find these WMPs. They think, well, if I look long enough and I take enough data, then even if the cross section, even if the probability the reaction happens is very low, eventually we'll see it. So who knows, maybe we will eventually find some dark matter candidates in these weakly interacting massive particles or something like it. Okay? And I've posted a link to an article if you're interested in further reading to see about what some of the candidates for dark matter are. Okay, so that's dark matter. Now back to general relativity, cosmology, and the fate of the universe. Okay, so just to remind you, we talked about general relativity in an earlier lecture, but general relativity is a discussion and a theory of geometry. Geometry is super important to the fate of the universe in cosmology. It can't be emphasized how important this is. But basically, in general relativity, the motion of the particle or a planet or a satellite or a person is determined by the properties of the space and the time coordinates through which it moves. So the presence of matter and energy causes the warping of the fabric of space-time. So for example, if you have a massive star or a planet, then it warps the fabric of space-time, locally curving space-time in towards it, and then anything around that planet or star follows the curvature, and that causes a gravitational attraction between particles with masses. Okay? So the famous quote from Minkowski actually says, "Geometry tells matter how to move, and matter tells geometry how to curve." It's a very beautiful statement of the theory of general relativity. Now this guy, Alexander Friedmann, he derived some equations from general relativity that laid the foundations for the Big Bang theory. Now, the Big Bang model relies on the general theory of relativity and the cosmological principle. So to remind you of the cosmological principle, that idea is the idea that the universe is isotropic and homogeneous. In other words, it looks roughly the same everywhere and in every direction. Okay? So if you look around here versus looking around on the other side of the galaxy, it will look kind of similar. So Alexander Friedmann, he was a Russian mathematician, and he solved the equations that I'm about to show you in 1922, and they laid out later the basics of the Big Bang theory that was developed in 1948 and on. So here's his equation, the Friedmann equation. So let me read it out to you. H squared is equal to 8 pi g rho over 3 minus kc squared over r squared plus lambda c squared over 3. Now to go over these things, the variables here, h is the Hubble constant, okay? G is, of course, Newton's gravitational constant. Rho, rho sub m here, is the average mass density of the universe. K is a curvature parameter of the universe, okay? So it tells you what kind of curvature the universe has to it. C is the speed of light. And it's important to emphasize here that the Hubble constant is not constant in time. It could have changed over the course of the universe. It might change in the future. And so we relate the Hubble constant to this idea of a universal scale factor, in your textbook called R, in a lot of other textbooks called A. But anyway, H is equal to 1 over R dr dt, okay? And it's really the rate of change of this scale factor that's important, not so much what it is in any given time. Okay, so that's the Hubble constant, that's the R. And then lambda is your cosmological constant that we discussed in the lecture on general relativity. And of course, c is the speed of light, like it usually is. So that's the terms in the Friedmann equation. Now, a little bit more about the Hubble constant. We've said that it's not constant in time. But if you assume it is for just a second, then you can use the inverse of the Hubble constant to estimate the age of the universe, okay? Now, various approximations in solving the Friedmann equation take k and lambda to be 0, okay? Lambda is pretty close to 0, as we'll see here in a little bit, and k, the universe is basically flat. Spoiler alert, sorry, but we'll talk about that more later. So you can get the age of the universe, a rough age of the universe, by looking at just this Hubble constant, okay? So if the universe has been expanding at a constant rate, then the inverse of the Hubble constant is the age of the universe. So the Hubble constant is 72 kilometers per second per megaparsec. If I do a little bit of dimensional analysis there and cancel out things and just get it in seconds, it would look like this. So you have 72 kilometers per second, 1 kilometer is 1,000 meters, and 1 megaparsec is 10 to the 6 parsecs, 1 parsec is 3.26 light years, and 1 light year is 9.45 times 10 to the 15th meters. So I end up with meters canceling out meters, so my distance part goes away. And that just leaves the seconds there on the bottom. So if I multiply by everything on the top, divide through by everything on the bottom, then I end up with my Hubble constant is 2.34 times 10 to the minus 18 inverse seconds. Now, if I take the inverse of that number, then I get a time. And that time is the estimate of the age of the universe. So that is 4.27 times 10 to the 17th seconds. And if you put that in years, it's a number that might look kind of familiar if you listen to the opening line of the Big Bang Theory, that little jingle. 13.6 billion years, okay? So there are corrections that you can do for a non-constant Hubble constant. However, it doesn't significantly change the estimates for the age of the universe, maybe just correcting it by 1-2% or so, something like that, okay? So there's your age of the universe, 13.6 billion years, inverse of the Hubble constant. Thank you, Hubble. All right, but back to the Friedmann equation. In order to use the Friedmann equation to determine the age and the fate of the universe, it's helpful to rearrange it like this. Let's divide through both sides by h squared. And then what we end up with is some terms that we'll call densities, okay, density parameters. So we end up with 8 pi g rho over 3h squared. That becomes our density parameter for the mass density, okay? Remember that rho sub m was the mass density of the universe. So there's our mass density term. Then we have kc squared over h squared. That should be an r squared, sorry. R squared, and that gives us our curvature term, because remember k was the term that related to the curvature of the universe. And then here we have omega sub lambda, that's lambda c squared over 3h squared. That's our Hubble constant there, and that becomes our dark energy term, which we'll talk more about in a minute. So the sum of these three things should then give the total density of the universe, omega. Okay, so let's look at this omega sub k. Well, what does this omega sub k actually tell us? Well, it tells us nothing less than the geometry of the universe. Now, when we discussed general relativity, we discussed the idea that space-time is a fabric that can warp, and warps in the presence of large masses, okay? So the idea is that if you have a star or a black hole, that causes a strong warping in the fabric of space-time, and that strong warping pulls objects into it. Now, I am not, for the purposes of this lecture, talking about that kind of local warping of the fabric of space-time. So it doesn't matter to me so much that a black hole over here is causing space-time to be pulled down over here. What I'm looking at is the space-time geometry for the universe as a whole, okay? So ignoring any effects of local curvature from, stars or black holes or even galaxies, what happens if you look at the geometry for the entire universe, okay? Okay, well, in that case, you can look at it as a quote-unquote closed geometry, which means that basically the universe closes back on itself, okay? Or it's an open geometry, where it looks more like a saddle, okay? If you were making a 3D analogy, it would look more like a saddle. Or there could be a flat geometry. In other words, it's more Euclidean in nature, okay? So these are the three possibilities. These three possibilities occur. The closed geometry occurs when omega is greater than 1. An open geometry would occur when omega was less than 1. And a flat would occur when omega is equal to 1. So that's the basic idea of the geometry of the universe. Well, by examining detailed maps of the cosmic microwave background, more about that in a minute, scientists have actually determined that K is very, very close to 0, okay? Hence, what that means is that omega sub K is very, very close to 0 within, say, a 1% tolerance. So what that means is our universe is locally curved due to massive or energetic objects like stars or black holes. But if you look at it as a whole, it's flat at large scale. So we live in a flat universe according to this value of omega sub K. Okay, so we live in a flat universe. So that leaves two terms in that Friedmann equation: the density from the mass and the density from the dark energy, okay? Now, the sum, this value of omega, total omega that we get from these two sums, is very, very important because it determines nothing less than the fate of the universe, okay? If your value of omega is much, much greater than 1, okay, for example, if you solve this Friedmann equation right down here and you solve it out for what happens when you have a value of omega that's greater than 1, this is usually done in graduate astronomy, astrophysics courses, okay? When you do that, you'll see that if it's greater than 1, then the fate of the universe is, it started off as a big bang, and it expands out, but then eventually the gravitational force is strong enough, and it'll pull it all back in, boom. This idea is called the Big Crunch, okay? In other words, the universe would sort of end the way it began, into a soup, a quark, gluon, energy, plasma, physics totally breaking down soup, okay? Ending the way it began. This also leads to the idea of the Big Bounce. In other words, it would end that way, but then there'd be another explosion, and you'd get another universe, and it would just keep on going, and going, and going, all right? Another fate of the universe could be if omega is basically equal to 1, or very, very close to 1. Then you get what's called the Big Freeze, okay? What happens then is that the universe is expanding, and it continues to expand at more or less a constant rate forever. And eventually, the planets, the galaxies, the stars, they all drift further and further and further apart from one another. All the fuel, the burning of the hydrogen, all that kind of stuff, eventually more stars aren't formed, and everything just sort of dies out. This is also referred to as the heat death of the universe, so that's the Big Freeze. Okay, finally is the Big Rip, okay? This is really scary but kind of exciting. In the Big Rip, you have an accelerating universe, okay? And eventually, the acceleration of the universe gets so large that it approaches infinity, and space is expanding almost infinitely fast, ripping everything apart, okay? So everything gets ripped apart there at the end. So that's the Big Rip, okay? So those are sort of the three possible fates of the universe that people toss about most out of all possibilities. Okay, well, I'm about to show you sort of a spoiler as to what the fate of the universe is, or at least what we think right now. But it involves telling you what the values for these densities are for the mass density of the universe and the dark energy density of the universe. So I'm going to tell you these numbers, and you might well ask, how the heck does she know that? Okay, well, how do we know this? There's been a couple of satellites that were sent up to measure in detail and map out in detail the cosmic microwave background of the universe. Okay, two of them, WMAP and the Planck. I'm going to talk more about the WMAP because it was the first one that went up. So the WMAP stands for the Wilkinson Microwave Anisotropy Probe, and it was a NASA mission and a spacecraft that operated between 2001 and 2010, and it mapped out the effective temperature of the cosmic microwave background radiation. So WMAP operated in a Lagrange point, which was 1.5 million kilometers from Earth. And a Lagrange point is really just a stable orbit point between two bodies so that it can just sit there, right, and go around and around without having to use up any fuel. So the Lagrange point was located here on this little diagram in orange, okay? And what it did is it sat in this Lagrange point, went in an orbit, pointed away from the sun, because of course that would mess everything up if it pointed at the sun, and it viewed the entire sky and figured out what the cosmic microwave background radiation was from the entire sky in a level of resolution that had never before been done. So what did WMAP give us? Well, you might have seen maps like this of the temperature of the Earth, okay, put out onto a map like this, where you have hot regions in red or orange and cold regions in blue or black, okay? Well, WMAP did the same thing for us, but for the whole universe, okay? Basically, it gave us the temperature of the universe in all directions. And of course, it doesn't vary much. So if you look at the scale here, it went from minus 63 degrees C to 37 for the surface of the Earth. Well, for the microwave sky, it goes from minus 270.4252 up to minus 270.4248. So it doesn't fluctuate much, okay? But you can see that there is a fluctuation, and it gives you these mass density, okay? I'm sorry, these temperature probes. Now, why would this help us? Well, if we know the temperature of the early universe, then we know its energy. And this would help us to figure out what the mass energy density is, that omega sub m. And that would help us calculate omega to great precision. Also, it enables us to calculate geometries in the known universe. Now, if you'd like more information about this, admittedly, I have to touch very briefly on these things in just this little lecture, but if you'd like more information, I've posted a link to a Physics World article that discusses it in more depth. Now, moving on to other terms in the Friedmann equation, since we discussed how we know what these values are, thanks to the WMAP and later the Planck satellites, we've been able to calculate what we think these omega sub m and omega sub lambda values are. So remember, lambda is thought of as the energy density of the vacuum of space, and it's the cosmological constant. And it was first introduced by Einstein in 1917 to achieve a static universe. And of course, he thought that was a huge mistake, a huge blunder, but it turns out we do need that term. We need that cosmological constant for an entirely different reason. Now we think that this value is positive. Now remember, I told you that it is really, really close to zero, and it is. Lambda is 10 to the minus 52 meters to the negative 2 approximately. So it's a very, very tiny little number. But even that very, very tiny little number gives us a dark energy density of 0.7, okay, or so. So this is what the Planck and the WMAP satellites were able to do for us. It enabled us to calculate these mass and dark energy density terms. Now, what would dark energy be? Well, one explanation for dark energy, and I'm quoting your NASA here, is that it's a property of space itself. Albert Einstein was the first person to realize that empty space is not nothing. Space has amazing properties, many of which are just beginning to be understood. The first property that Einstein discovered is that it's possible for more space to come into existence. And then one version of Einstein's gravity theory, the version that contains a cosmological constant, makes a second prediction, that empty space can possess its own energy. Because this energy is a property of the space itself, it would not be diluted as space expands. As more space comes into existence, more of this energy of the space would occur, and as a result, this form of energy would cause the universe to expand faster and faster. Unfortunately, no one understands why the cosmological constant should even be there, much less why it would have exactly the right value to cause the observed acceleration of the universe. Now, also from these WMAP and Planck satellite measurements, we were able to determine what omega m is. Now it turns out you can rewrite omega m in terms of a ratio of the mass density of the universe to a critical density, a so-called critical density, which encompass the other terms in that term in the Friedmann equation. So this critical density would be 3h squared over 8 pi g, and if you solve for it, that's 9.8 times 10 to the minus 27 kilograms per cubic meter, okay? Now, that's not a lot. Okay, if you remember what the mass of a proton is, okay, then you know that this is only a few protons per cubic meter. It's not a lot. However, The observable mass in the universe suggests a density much lower than this. All right? So according to WMAP, the ratio of the observed mass of the universe to the critical density of that mass is 0.3. Okay? So, not a lot. Now back to the Friedmann equation. If you plug in for it, omega sub m is about 0.3, omega sub k roughly 0, and omega sub lambda about 0.7. So to summarize from WMAP and later from the Planck satellites, what this means is that ordinary baryonic matter, the stuff that you can see with your naked eye, stars, planets, things like that, makes up only about 5% of the density of the known universe. So everything that you're seeing and touching and interacting with on a daily basis is actually not really ordinary if you think about it, but kind of extraordinary if you think in terms of the total amount of mass in the universe. 5%. Dark matter makes up about 24 to 27%, depending on which satellite you look at, of the density of the known universe. And dark energy makes up between 68 and 71 or 72% of the density of the known universe, depending on which satellite data you look at. Okay? I would like to add that the Planck satellite is higher resolution and corrected the values by a few percent, and so those are the ones that people usually cite now. 5%, 27%, 68%, those are the numbers for the ratios. Also, from these satellites, it tells us the universe is basically flat. There's local curvature of space-time from stars, black holes and all that, but it's not a universal curvature. So what this tells us is the universe will expand forever and maybe speed up a little bit as it goes, because right now we think omega is slightly larger than 1. So the curvature is flat, which means its geometry says it should expand but not accelerate. However, due to the size of this dark energy term, the dark energy is causing it to accelerate despite the curvature. Now there's also a problem in cosmology that's called the horizon problem. And that's kind of this. The observable universe, or the known universe, is made up of all of the things that we can see from Earth. And this has a radius of about 45 billion light years. And everything looks pretty much the same in every direction. So what this means is it would make regions in opposite sides of the sky about 90 billion light years apart. But the universe is 13.8 billion years old. Well, maybe you see one problem straight off the bat if you just give it a second's thought. 90 billion light years apart in a universe that's 13.8 billion light years old. Speed is equal to distance divided by time. Well, let's look at Hubble's law, too. Hubble's law says that the recessional speed v is equal to the Hubble constant times the distance of that object from us, d. Okay, so if two objects are on the opposite sides of the universe so that they're 90 billion light years apart, well, 90 billion light years is about 27,600 megaparsecs, okay? So we'll put that in for our distance d, and then we'll multiply that times our Hubble constant, which is 72 kilometers per second per megaparsec. And if we do that, then we get 2 million kilometers per second for the recessional speed, which is 2 times 10 to the 9th meters per second. And the speed of light is 3 times 10 to the 8th meters per second. Whoa. So, what that means is that objects at opposite side of the known universe are moving apart from one another faster than the speed of light. Well, relativity restricts the speed of objects moving through space. But space is space. So it's not moving through space because it is space. So that means that space can expand as fast as it wants. Space does what it wants. Sorry. Anyway, this is also surprising that things that far apart look the same because they can't communicate using a signal that's transmitted at the speed of light. In other words, you wouldn't think that, for example, two teenagers would be wearing exactly the same things unless they were looking at the same media and, worshiping the same Katy Perry idol or whatever, right? Otherwise, they wouldn't all be wearing those same outfits. They have to be able to communicate. Well, this idea is sort of explained by a theory right now that's called inflation, okay? The idea of inflation is this. In the early universe, there was a sudden rapid growth, as much as 50 orders of magnitude, in a short amount of time between 10 to the minus 35 and 10 to the minus 32 seconds after the Big Bang, Okay? So in other words, everything was kind of all together, and because it was all together, it was close together so it could all talk. But then at some point, it expanded really fast by a bunch. Okay? Now, sometime after inflation, the universe then grew too big to communicate with light signals or anything traveling at the speed of light again. But uniformity had already been achieved by this time. Okay? So at that point, what that means is that everything already kind of looked the same before it got too big to talk to each other. So inflation also can help explain how the universe can be older than the value predicted by taking the inverse of the Hubble constant, because the Hubble constant wasn't always the same. Okay, well, I said we'd get back to the fate of the universe, so here it comes. If you look at that plot of the average distance between galaxies versus time again, okay, what we think might happen is that we're here. We're this yellowy orange line, okay? So we started off with a Big Bang, and then the distance between galaxies got bigger and bigger and bigger, and now we're accelerating and getting further and further apart with time as time goes on. So we live in an open, relatively flat, accelerating universe. The most distant galaxies recede from us at speeds greater than the speed of light, because space can travel as fast as it wants. As the universe ages, we will see more things for a while, because the light will have time to reach us. But eventually, our observable universe is going to start to shrink, because those objects are traveling away from us at speeds greater than the light that they emit. And the limit for this is thought to be about 62 billion light years. So the furthest we'll ever see into the known universe is 62 billion light years. And then after that, because of the acceleration of the universe, we'll start to see less and less and less and less as we drift apart. Okay? So that relatively depressing note is where I leave you from this class. I hope you enjoyed it. And I highly encourage you to look at the Crash Course Astronomy videos, which I've posted beneath, because that guy is way more entertaining than I could ever hope to be. So, good luck. Let me know if you have any questions, and I hope to see you around.